Okay, good evening, friends. So today we are going to, I'm going to speak about this application of voltammetry in organic analysis, and then we discuss about the application of thermogrammetry, differential thermal analysis, and differential scanning calorimeters and thermometric titration. Basically, today we are going to cover both this the analysis of the various analytes using these electrochemical techniques and then the thermal analysis. Basically, in case of this electroanalytical technique, we are just going to cover this voltammetry and polarography. And just before going to this voltammetry and polarography, I'll just discuss this some basic terminology in the electrochemistry so that the people who are not belongs to this particular sections they will understand that what we are talking it, and then we discuss about this thermo analysis based on the thermal analysis. So as before, so let's do the recap what we have done so far, because all these things are interlinked, so it's always better to have some recap. So that's why I always give about say 15 minutes time to do all this recap, and then some of the major terms and the technique we can cover, because some of the people who are going to attempt for the assignments or maybe opting for the exam, it's really helpful for you people. So analytical terminology is we have seen that we have discussed the sample, which is nothing but say composition of analyte and the matrix. Analyte is nothing but the element which we are targeting for the analysis, and matrix is whatever the except analyte, everything will be considered as a matrix. And then we have seen the various terminologies like PPB, PPM, and then the sensitivity of the instrument, how to define the sensitivity of the particular instrumentation. That is nothing but the slope of the calibration curve. And then we had discussed the type of analytical techniques. So this is very important, I think, for all of you. At least if you get this kind of a terminology in your mind, it will be very helpful for you, because then you will come to know whether you are dealing with the absolute methods. Absolute methods are nothing but the analysis which does not depend on any kind of a CRM or SRMs, or even in-house reference material termed as a absolute analysis. And the best example for this is the gravimetry. And then we discuss the relative methods. The most of the, as I told you, about say 60 to 70% analysis are basically of this relative methods. Once we talk about the relative methods, it means that you are doing whatever the measurement you are doing, they are with respect to relative. So basically, for this determination, you have to prepare a calibration curve, and this calibration curve is prepared by using the standard solutions. So with respect to those standard solutions only, that you will come to know that whether this absorbance, intensity or counts are coming, it belongs to what concentration. Okay, then we had talked about the comparative methods. See, difference between the relative method and comparative method is that in both the cases, though we are preparing a calibration curve, but in case of the relative methods, we are using any kind of a standard solutions. But in case of a comparative method, it is most necessary or is essential. One of the essential requirement is that the calibration curve you have to draw with the help of a matrix matching standard only. For example, if you are doing the analysis of the copper in an alloy sample, then you have to prepare a calibration curve by using a copper, different concentration of a copper in a metals only, alloys only. And if you are looking for the any kind of a natural matrix like vegetations, then you have to take the concentration of a copper in any kind of a vegetation solvent. So that is the difference between the relative and the comparative methods. Then we talk about the solution and the stoichiometry. So in see stoichiometry, because with time you may be just forgetting how to write in a chemical equation. So that's why we have taken up this particular section. So in this small section, we have seen that how to balance a chemical equation, and whatever these things had been given in the parentheses, it just show the physical state of the metal. Basically, if it is S solid and G for gases. And similarly, the coefficient which you use in the equations, they are just to balance the equations, because you are the right hand and left hand side of the equation have a same number of atoms of a particular molecules. Then we have discussed the the how the improvements in the analytical chemistry happens from the gravimetry to the calorimetric and then to spectrophotometry. See, gravimetry, there is a certain issues are there because you cannot perform the gravimetry analysis for all kind of samples, and the utmost condition of the gravimetric analysis that you have a concentration in the percentage levels. If it is less than a percentage level, we are going to end up with the erroneous results. So this problem has been resolved by using the volumetric technique, and then volumetric technique means acid-based titrations or the redox titration. And today in lecture we see the thermometric titrations also. And those again further improvement has been bring by using the calorimetry, because if you have a very small concentration of elements are there, so a color can be developed, and with the help of that color one can identify, not only identify but the quantify also your element of interest. Then we have looked about the importance of sampling. See, again, I'm telling you, sampling is one of the most crucial part of the analytical chemistry, because if you are not collect your sample properly, or if you have done any major errors while collecting a sample, whether your sample is a natural origin, environmental sample, or even if it's synthetic origin also. Okay, until unless you are given the, for example, if you synthesize a 100 milligrams of the any compound, until unless you are using whole 100 milligram of the samples, then there is no issue. But if you are giving a sum for some different analysis, only a few 10 milligrams or like 15 milligram, then one has to be very careful while choosing the sample out of the your bulk samples. Then we have discussed the importance of sample storage. The sample storage, I told you, is very important. Again, it's a very crucial step, because during this transporting and storing, because it's not always possible that you collect the samples and do the analysis on site. It is not possible in most of the cases, because there are certain cases are there where portable instruments are there, so analysis can be done on site also. But generally, we bring the sample to the laboratory and then keep it for some time. So during this process of transportation and storing, we should not lose the element of interest, and especially this is true for a volatile element, as well as because of the container of the walls may sometimes you can those element of interest will be get absorbed or adsorbed, or sometimes and many things will come from the container also. So that's why very important. Then sample digestions. See, sample digestions is again one of the crucial step. See, during the sample digestion, the analyst, the responsibility of the analyst to see that he had completely taken out the analyte from the matrix. And for that, we have discussed the various procedures are there, and then it depend on the what kind of instrumentation and what technique you are going to use it. So depending on those instrumentation and technique, that the extraction of the analyte from the matrix is differ. And some of these common techniques is like dry etching and then wet etching. And so we have discussed it, and this wet etching can be done by using the conventional heating on a simple hot plate, or it can be done by using the microwave assisted digestion, where the microwave used so that your digestion becomes much faster. And then in that process, I see, especially in case of volatile elements, so what kind of a chemistry has to be done, and wet digestion has to be done in which way, one has to look it. Then we discuss the intricacy with the environmental analytical chemistry, in which I just want to stress. See, in case of synthetic sample, you know the origin of the samples, and generally we deal in a large amount of sample, maybe about say 1,000 ppm or maybe 10,000 ppm, from 1% to maybe more than that. But in case of environmental sample, generally the over concentrations in ppm to ppb and sometimes sub ppb levels also. Then we discuss about the separation chemistry. Separation chemistry will cover this solvent extractions, ion exchange, and then we discuss about this chromatography. So various kind of chromatographies are there, and then in this we had given this test on this post gas chromatography and the HPLC, and we have seen that based on this stationary and mobile phase, which is the most two terms are there. On that basis, one can, distinguish various spectroscopies are there. And see, one of the most important things, I think, when we discuss about this gas chromatography, the gas chromatography is the only technique where the analyte does not interact with the stationary phase. So generally, in case of a gas chromatograph, we have seen that the carrier gas, we use either helium or a nitrogen. Basically, inert gases are being used so that there is no interactions. And then we discussed about in the last lectures about the atomic spectroscopy. Not only atomic spectroscopy, we have covered some part of this molecular also. In that we have seen the UV visibles. So basically, it has been started with the Bohr, which has given the concept of the atomized quantized energy levels, and on that basis, it has been this discovery of the spectroscopy, and basically which we use in analytical chemistry is a spectrometry, in which we measure the intensity by using various kind of detectors. Okay, that we have seen that this can be a PMG or a CCD, or nowadays CID also has been used. So in this we had discussed much in both absorption spectroscopy. We had covered this flame atomic absorption spectroscopy and a graphite furnace atomic absorption spectroscopy. In both of these cases, the basic difference is that the atom cell, in this case of flame, it is basically flame. So there we have seen that we are using the two different kinds of flames, that is the acetylene and oxygen, when we need a temperature about say 2300 degrees centigrade. And then we have seen when we need a higher temperature, then we are using this acetylene and nitrous oxide, where we can reach the temperature of 3300 degrees centigrade, and all this temperature required because ultimately we need atoms actually. So those are, in some compound, it is not possible to break that molecules into the atoms at a lower temperature. So that's why we need high temperatures by using the nitrous acid flames. And then we are having this graphite furnace. See, what is the basic difference between the graphite furnace and all these things? The sensitivity is there. High sensitivity we achieve in case of graphite furnace. And one of the more major advantage, which I do not know whether you had able to capture during my that lecture. See, major difference is that, if you have very small volume, and this is especially true when we are analyzing the various kind of biological fluids, because many of the doctors they're interested to know this what are the heavy element concentration in the various biological fluids which we taken out from the patient. Well, in that case, graphite furnace is very useful because the volume requirements may be about say 10 microliters, and which is not possible in case of FAS. And then we have seen the various kind of interferences which is coming in both the cases. That is the how to correct this background absorptions. So we have seen the continuum source corrections. Then we have seen the G-man corrections, and then the Smith-Haffey correction. But as I told you, Smith-Haffey corrections need a lower and higher current. Actually, and a high current, we are just spoiling our filaments of the cathode, of this hollow cathode lamps. So that's why we just try to avoid it. So but only this continuum source correction by using the deuterium lamp, and then G-man corrections these are the two important corrections which is one used to do it. Then one we have seen other thing which we have seen this ICP-OS, and basic difference in the ICP-OS OIS that here again the temperature is more than the analytical zone. Basically temperature go up to 10,000 Kelvin, but we do most of the analysis in about say 5,000 to 6,000 Kelvin. And here we can do the emission line because it's basically first this FAS and GFAS, they are the absorption technique and generally governed by the Lambert-Beer law. Whereas ICP-OS is the emission techniques there. Okay, and in this both we can use the emission line of both of the atom as well as the ions. That's why many times this question comes because earlier people used to use the ICP-AES, but now we use the word of the OES, because once we use the OES, it means that we are having a provision of detecting both the emission line from the atom as well as the ions are there, and how the atoms have been produced from a matrix, from a different matrix, either solid or liquid. We have seen also during this course of lectures. Then we discuss something about the mass spectrometry. The mass spectrometry is nothing, in this case, the separation is based on the M by E, that mass by charge ratio. So first thing is that ionization, and after doing the ionizations, there is a way to take it into a magnetic field where the various kind of, the ions will be deflected as per their mass by charge ratios. And then we have seen the various kind of detectors that we have seen I think some 4 or 5 detectors are there during this course of lectures. Now coming for the today's lectures. Today we are going to discuss about this basis of electrochemistry. And then electroanalysis. Today, basically, we are going to discuss electroanalysis. But before going to electroanalysis, we just go through some basic terminology of the electrochemistry. And then in the electroanalysis, there's conductometry, potentiometries, and colorimetries and voltometry. And in some detail we use, because both the uranium and anthracene, they are one of the inorganic species, or the organic species. How to do the determination of the uranium and anthracene by using the voltometry technique also we will discuss today. And then the thermal analysis, we discuss the basics, and then both this TGA, DTA and DSC, and we are going to end up with the thermometric calculations. So let's see. See, I think most of you must be aware what is electrochemistry. Electrochemistry basically is the study where the production of electricity from energy released during a spontaneous chemical reactions, and use of electrical energy to bring about a non-spontaneous reactions. So basically in the galvanic cell, what is happening? In a galvanic cell, a spontaneous chemical reaction is going on, and that will generate a current, and we will term these as batteries. Whereas in case of various kind of electrolytic cells, there's you have seen that plating, zinc plating or chrome plating in many places. So what is happening there? We consume the electrical current to bring out the non-spontaneous reactions, and while using we do the various kind of electroplating. That is called electrolytic cells. So in this, basically anode is nothing but the electrode where oxidation occurs, where basically loss of electrons, and cathode, the electrode where the reduction occurs, the gain of electron. And generally a salt bridge, a device used to maintain a electrical neutrality, and through a circuit, that is the electron flow always from anode to cathode through a wire. So as I told you, this cathode is nothing but the gain of electrons, and anode where is you are getting a loss of electrons, there is the oxidation going. And this is generally, can we remove it for some time? This one.
Click over it. Click on it.
Okay. So So this is basically a Daniel cell. So how the Daniel cell looks like, the electrode of a zinc and a copper dipping in their respective salt solution. Means that the zinc electrode has been dipped in zinc sulfate solution and a copper electrode in a copper sulfate reaction. And what is happening during this in the Daniel cells? Okay, so in this the zinc is coming from the metals to the solutions from the electrode, and whereas in the other side where this cathode is there, that this copper ion going back to the copper cell, that particular electrodes are there. So there is one side the zinc sulfate solution, other is a copper sulfate solution, where we are maintaining the circuit of this thing. This is the electrolytic cells. So where the electrolysis of molten sodium salt, sodium chloride is carrying on. And basically, as I told, this is a non-spontaneous reaction. We are converted to a spontaneous reactions. And with the help of electrical energy. And this all the electrical energy help to convert this non-spontaneous reaction to the spontaneous reactions. And we are converting this chemical electrical energy into a chemical energy. Okay, and then this that's what it has been shown here. And conductions in the electrochemical cell is the external connection, that is only movements of electrons through the external wire. Then within the solution, migrations of cations and anions take place, and at the electrode surface, both the oxidation and the reduction reaction. And these are the general standard cell notations are there. So whenever single line is there, represent the phase boundary. Basically, whenever single line you have seen that it represents the phase boundary. That is the zinc, which is a solid, and the zinc in a +2 state, that is zinc sulfate solution, of which only 1 molar. And that has been denoted by a salt bridge, because two lines represent a liquid junction, which is nothing was called as a salt bridge. So this is how the various notation when we are writing any kind of a cell reaction. Sorry. Now, so this is this is very basic how to before going to the technique of electrochemical technique for measurement of the various kind of analyte, and in this case, Nernst equation. The Nernst equation is nothing but the in an equation that relate the reduction potential of electrochemical reactions to the standard electrode potentials. Okay, so nothing but a electrochemical relate the reduction potential of electrochemical reactions to the standard electrode potential reaction, that is E and E naught, and temperature and activity of the chemical species undergoing reduction and oxidations. And basically, this equation was named after Walter Nernst, a German physical chemist, who formulated this equation. A quantitative relationship between the cell potential and the concentrations of the ions is, for example, this oxidation species, and then it's gaining electrons, and then we get the reduced species. And for for evaluation of this Nernst equation, the standard thermodynamic has been used. That is delta G is equal to delta G naught standard RTLNQ, where QR is the reaction coefficient. And then putting this delta G is equal to, that is the standard Faraday equations, and equating to this equation, putting those values in this thing, we are getting this relation, Nernst equation, which relate the electrochemical reaction to the standard electrode potentials. And so these are the activity of the reduced species and the activity of the oxidized species. And R is nothing but say universal gas constant. And now this, what is the electro analysis? See, measure the variation of the what is happening in the electro analysis. Measure the variation of the electrical parameters, maybe it's potentials, current, charge, or conductivity, and then this relate to a chemical parameter. Chemical parameter is nothing but here in our case is a analyte concentration, because on all our cases our interest is to just to know the concentration of the analyte. And what are the instruments which can be used? Conductivity, potentiometry, and coulometry, voltometry. So coming to this part of the voltammetry polography, which is the we are going to discuss in some details. See, measurement of current as a function of voltage under non-equilibrium conditions, and is use a polarized microelectrode for measurement, and scanning of voltage allow more than one analyte to be determined at once, because there is a solution, there are more than one analytes are there, so it can be determined at once and can be used for both aqueous and non-aqueous solutions. Generally, when the electrode is a mercury, it will be termed as polography, but we will see in detail also. Although an electrochemical cell need only two electrodes to operate, and it is very beneficial to introduce that's why third electron has been introduced, that is known as a reference electrode, and that is an electrode which has a known and a fixed electrode potentials. And no current should ever pass this electrode, as a current would change this potential and possibly damage the electrode. The reference electrode is used to control the potential of the working electrode by measuring the voltage between these two electrodes. The techniques what we are using is polography. The polography is nothing but uses a liquid dropping that is a dropping mercury electrode, or a static mercury dropping electrode, that we termed as a SMDE. DME means dropping mercury electrode, whereas the SMDE is static mercury dropping electrodes. Whereas in case of voltammetry, use a stationary electrode, that is a hanging mercury dropping electrode, or a rotating disc electrode is there. Friends, if anything is there, you can just ask me anything. And I'm sure that if some queries are there, I will try to, I'm telling you, I'll try to answer here itself. If I do not know, I will take the help of my colleague, which are the expert in this field. So please, be free to ask anything during the course of the lecture, because whatever question you will ask, it will be going to reflect it in our chat box. And by looking the chat box, I will understand that you have some queries are there. So please feel free to ask anything. So these are the various types of voltammetry techniques are there. And then it's already all details are there. You can go through whenever you have a time. The linear strip voltammetry, staircase voltammetry, and cyclic voltammetry, anodic stripping voltammetry, cathodic stripping voltammetry, adsorptive stripping voltammetry. This is adsorptive stripping voltammetry we discussed today in both the cases, the anthracene as well as in the case of the uranium determinations are there. Okay. And since uranium is very important as far as the Department of Atomic Energy is concerned, so with the help of this technique, we get a very reliable result, even less than 1 ppb. And what is this technique? Is similar to both the anodic and cathodic stripping voltammetry, except that the pre-concentration step is controlled by electro analysis, and the pre-concentration step in the adsorptive stripping voltammetry is accomplished by adsorption on the working electrode surface, or by reaction with a chemically modified electrode. So here what we have done in case of a uranium, we have done the depositions of this chloroanilylic acid, and on the chloric analytic acid on the working electrode, and where we had done the selective adsorption of a uranium. That is we call as a pre-concentration. And then polography, also some of these things we discussed in the polography, and rotating electrode voltammetry. And then the other three forms are the normal pulse voltammetry, and the differential pulse voltammetry, and chronoamperometry. Okay, so what is happening in case of polography? See, polography is considered the reduction of the metal ions at the mercury electrode. What is happening? That amalgam, the metal is forming amalgam at the with the mercury, and as the voltage is swept, the current will remain constant until the voltage is sufficient to drive the above reaction, and then current will increase to reach the limiting value. So if you see there, if you draw the current versus voltage curve in this case, so basically there is some this current will be appear in the beginning itself, but that is we call this as a residual current, and the reason of the residual current is basically comes both the condenser as well as the Faraday currents are there. And in this polographic wave, this small current flow in the beginning is known as a residual current and is carried by the supporting electrode and the impurities present in the sample also. And then how to evaluate the diffusion current? Diffusion current is nothing but that is the limiting current minus the residual current. This is a very important equation by which the diffusion current linked with the concentrations. So that's called as a Ilkovic equations. So Ilkovic equation in the relation used in the polography relating to diffusion current and the concentration of the depolarizer. Depolarizer is nothing but the concentration of my analyte, and which is the substance either reduced or oxidized at the dropping mercury electrode. And these are the how we find these Alcovic equations. That is, ID is equal to K and D 1 by 3, raised to power 1 by 3, M raised to power 2 by 3, and T raised to power 1 by 6 into C. And in this case, where K is a constant, which includes Faraday constant, and has been evaluated and has two values at 708 for maximum current and 607 for the average current. So whenever any evaluation has been done, it has been predefined that whether you have done that concentration evaluation at maximum current or at the average current. So in case of average current, you have to take this value of the K 607, whereas for the maximum these are the values can be 708. And the details of this can be read in any standard textbook, which it can be written about the electrochemical analysis. And D is the diffusion coefficients of the depolarizer in the medium, that will be termed as a centimeter per square second, and is the number of electron exchange in the electrode reaction, and M is the mass flow rate of mercury through the capillary, that is given in a milligram per second, and T is the drop lifetime in second, and C is the depolarizable concentration in general, say millimoles per liter. So this is how the Ilkovic equation is there, and this actually most of the even if you are preparing any kind of a competitive exam, and various question had been framed on the basis of these Ilkovic equations, where one has to various values had been given to you, and then you have to evaluate the concentration of the analytes are there. And the second very important terminology in this electrochemical analysis is the half-wave potential. See, half-wave potential basically when we draw a current versus voltage curve. Okay, so there you will get in a this polography wave current we said it, and then this half-wave potential is basically the characteristic of the element actually. It's not only characteristic of the element, but its chemical form also. So that's how, because the electrochemical technique is the technique. Here not only we can determine the concentration of the analyte, but we can determine its chemical forms also. Okay, why? Because this half-wave potential is a potential at which the polographic wave current is equal to one half of the diffusion current. Okay, this is one half of the, because this is a limiting current and this is a residual limiting current and this is a residual current, and half, this is how we evaluate this half of the diffusion current. So half-wave potential is a potential at which the polographic wave current is equal to one half of a diffusion current, and a given supporting electrolyte, the half-wave potential is unique for each element. Okay, and then it's most important is it's not only unique for each element, and it's different balance state and chemical forms. See, different balance state and the chemical form. So these are the very important. It's not only for the element, but is that element. For example, arsenic 3, arsenic 5 is there, chromium 3 and chromium 6 is there, and then it's having various kind of chemical forms also there. So those can be having a different half-wave potentials. And observation of a current peak at a specific half-wave potential will help in identify the chemical species that producing that current. So on that basis, one can identify not only the element but its chemical form also. Okay, and if there is a second element, for example, if there are number of elements present are there, so when in the current voltage curve you will have a second wave also, and again that also will have a half-wave potential is there. And so that's how we, and if there are more number of elements, so similarly there will be others, and each elements having its characteristic half-wave potentials are there. On the basis of that, we can identify and quantify the elements actually. Quantification again, I'll tell you, again has to be done on the basis of the calibration curve. So we has to take it to various concentration and then do the photography and then draw a calibration curve of the concentration versus current. So there are certain problems, this problem associated with the classical polography, because this we termed as a conventional or a classical polography. What are these constraints on this thing? Reticle control could be achieved especially in relation to the size of the drop of mercury. And variation in size as drop were formed meant that the limiting current fluctuated, which limiting is sensitivity. But for example, the technique, because we are talking about this polography has been developed in the, maybe in 1950s onward. And then at that time when the other techniques comes in the, FAS is nothing but the flame atomic absorption spectroscopy, where we have a detection limit of the ppm, and sometimes if more sensitive elements are there, we can go in a less than a ppm is very near to ppb range also, about say 100 ppb. Okay, so those techniques becomes to very sensitive. So in that case, the utility of this polography, this classical polography, is very limited. And why this limited? Because resolution very poor, and difference between the half-wave potential need to be greater than 0.2 volt for different analysis. If it is less than the 0.2 volts, it's not able to resolve. It's not possible to resolve the two different analytes. So that's why these are the limitings, both the size as well as the voltage. This thing. Then how to improve this improvement, how we have bring out the improvement in the classical polography. So this has been improved by improving the techniques by which we are doing the current sampling while doing the giving the various voltage, that is the pulsing voltage actually. So improvement arose through the use of a microprocessor which will allow to the current sampling and a voltage pulsing. The current sampling allowed measurement to be taken when the drop was fully formed. Okay, and in addition, measurement be taken just before and after. Actually, we will show you in the next PowerPoint how what is mean by this sentence is actually. And in addition, these two measurements should be taken. Then we will see that before pulsing and after finishing this, suppose we are giving 50 millivolt pulse is there. So you can take the measurement of the current before and after that, just finishing the drop. And then, in addition to this voltage pulsing, big improvement in the resolution, that is brings about, you see, from the 0.2 volts, we have come out the less than a 0.05 volt. So that's how we had improved the detection capability in the electrochemical systems. So that's what the meaning is there. See, first measurement we have seen, see, this is basically voltage versus time plot is there. So in this, we have seen the first measurement, we are giving the 50 millivolt pulse is given. So first measurement we had done 50 before the pulse, and the second measurement 15 millisecond before the end of the pulse. And when we plot over differential current, produce a peak whose height is related to the concentration and whose maximum is nothing but a half-wave potential. So this is how we are bring the improvement in the classical polography. Okay, this is just simple principle of polography based on against say Ohm's law. Now here we are having, instead of it 2 electrode, we are having a 3 electrode systems are there. So one is a reference electrode, a working electrode, reference electrode and a auxiliary electrode. Now we will see that what kind of function of these electrodes are there. And then there's a multi-mode electrodes are there. So this is how we produce these dropping mercury electrodes. And there how we produce the static mercury drop electrodes. And now there's, the variations are there. And this is called as a hanging mercury drop electrodes. So we produce this stable surface, and then here the hanging mercury drop electrode, the time for this stable surface is even more. So reference electrode is nothing but is a silver chloride and potassium chloride. There is about the 3 moles per liters, having a concentration of 3 moles per liters. And auxiliary electrode in general is either say platinum one or the glassy carbon. And actually, this is whether we have a platinum or a glassy carbon that depend on the application. What kind of application, what kind of analysis we are going to take it. So depending on that, we can either have a platinum or a glassy carbon electrodes. And these are basically this way to apply the voltage various the mode way to apply the voltage, and this is basically in case of the direct currents are there, and then this is the current voltage curve in case of that will be resulting curve. See, this is a very crucial and important actually. See, what kind of a working electrode one has to choose is whether one has to go for the dropping mercury electrode or the static mercury drop electrodes or hanging mercury drop electrode or rotating disc electrodes are there. So again, it depends on the concentration of the analytes are there. If we are dealing with the concentration of the analyte in the ppm range, then there is a better to go for the dropping mercury electrode. See, there is no harm you can do by using, but why to go for a more tedious and expensive one. So you choose a dropping mercury electrode is more than enough when we have a analyte concentration in the ppm range. And a low ppm range in that case is better to use the static mercury dropping electrodes. And when we look for these traces that is in a ppb or the ppt levels, then one is to go for either to a hanging mercury drop electrode or a rotating disc electrodes. Okay, the choice of electrolytes. Often a buffer is used. I'll show you in when we are discussing about the analysis of the uranium by using the anodic stream volumetric. What is the importance of a pH actually? Because they are the some of these things are very pH sensitive. Then it's because it allows the signal enhancement as well as increase the selectivity and some cases masking of elements also, which we do not want to. Some of the interfering elements can be just masked. See, in case of polography, what is happening? This is the reduction. That is the metal ion reduced to the metal stage, and then we are carrying out the measurements. Then stripping volumetry. In this case, the formation of the first step is the amalgam will form where the metal will be reduced to its state, and then we do the extraction, and where again it will be formed in metal ions are there, and then we can measure the current produced. Whereas in case of adaptive stripping volumetry, see, you have seen both the difference. See, in case of a stripping volumetry, here the amalgam formation with the mercury, but here that we do the pre-concentration. The pre-concentration of the nickel has been done on the dimethyl glycine, and from the nickel dimethyl glycine, then we will extract back these metal ions. So that's how we increase the detection limits. So this is an example where we discuss about the anodic stripping volumetry, and here we are considering the 3 analytes, that is the zinc, cadmium, and copper. Okay, so the zinc will be reduced to zinc. And this is the standard reduction potential, that is minus 1 volt minus, and then cadmium minus 0.6 volt, and copper minus 0.2 volts. Now, suppose if we are having a mixture of all those things, so how to do it actually, go about the analysis. So this is the procedures are there. Firstly, whatever the sample is there, you bubble it through the nitrogen to displace all the oxygen. Because it will help us to avoid the many interferences, and then apply voltage of a minus 1.2 volt. Once you apply minus 1.2 volt, all will be get deposit on the mercury, and then we carrying out this stirring, because stirring is very important during that analysis. So stirring should not be stopped. Continue the stirring throughout the deposition range, and then stop the stirring and scan the voltage from minus 1.2 volts to 0.0 volt. So what kind of a graph you will get it? So this is the you will get a graph, and then you will come to know this is the current versus voltage graph is there, potential, and then you will get the concentration of the zinc, cadmium, and copper, and then the as per the knowledge of the reduction potential, you will come to know the quantify the both quantify as well as quantify as well as the uh, you can do the qualitative and quantitative analysis of the zinc, cadmium, and copper. And these are some of these comments which when we are using any kind of stripping there. So deposition time can be varied a longer time for lower concentrations that depend on the what kind of a concentration you are dealing at. If you are a pre-end knowledge that you are looking for a low concentration, then you can increase your deposition times. Okay, the deposition voltage selected to ensure that all the analyte can be deposited on the hanging mercury drop electrode, and the use of stripping allow detection at a ppb level, but should not be used for a high concentration, because if you use high concentration, because your that is electrode will become saturated, and this selective deposition may result in that case actually. And in stripping stage, the direction of the reaction is reversed. For example, zinc, cadmium, and copper are released into the aqueous solution in the example. So the reaction must be a reversible reaction is there. So that also has to be taken care. That reaction should be a reversible. So this is how what we do. I told you that being from this Department of Atomic Energy, this analysis of the uraniums in the various affluent samples or in any groundwater samples or potable water is very important for us, and where we need a detection in the ppb levels. So this is how this ultra-trace concentration of the uranium has been determined by using the adjusting stripping voltammetry. And in this, we have used the reference electrode silver chloride. Auxiliary electrode was a platinum one, and working electrode has been used as a hanging mercury drop electrodes are there. And in this case, we had used this 50 millivolt pulse, and a pulse time is given 30 millisecond, and a potential step over 4 millivolts actually. And in this, we reach the detection limit of the 0.1 ppb. So these are, where various steps are there. So first, the uranium gets selectively adsorbed on this hanging mercury drop electrode by in this chloroanionic acid. And so uranium chloroanionic acid complex will be get deposited, and then we will strip uranium out of this complex. And in the second step, see, these are the various parameters actually. See the pulse time, conditional voltage, durations, steering of the state of during conditioning, and deposition potentials and durations, steering of the during deposition, equilibrium time, measurement cell of after measurement, modulation time intervals. See what I want to show you here, this pH. As I told you, this is a very, using the buffer or using a very concentration of the acid to maintain the pH at a particular, when we are doing especially the any adsorption we are carrying out by using any complex, because that is very sensitive. Those adsorptions are very sensitive to pH sensitives are there, and this is how we can show you here. You see that here. See, for example, this basically is about the 1.8, pH is about 1.8. So you can see that if you are having the pH even more than less than 1.8 or more than 1.8, in both the cases, the concentrations are the detection limits are very, very poor actually. So we can that will be reflected in this peak height. So this is how we do the calibrations. So as I told you that every instrument need a calibration. So this is the calibration has been carried out in this in the two different range, because once we do the analysis a 0.1 to 1 ppb, and other calibration is shown the 2 ppb to 8 ppb. See, it's not necessary that you use the 2 to 8 ppb and then you are looking for some concentration in the range of a 0.1 to 1, because that your RSD values, so the uncertainty will be very high compared to if you are having a proper calibration curve is there. And this is how we do this anthracene. Anthracene, is very, again, it's a very crucial compound which we want to know the concentration in the various kind of potable waters. Basically, anthracene is a skin allergen. Because of this concentration, various kind of skin issues will be come up, and of course can be done by using the gas chromatography or the mass spectrometry. But again, this use of this voltometry is a very handy one. And in this, what we do, this electrochemical method for the detection of retained synthesis in water. In this, the working electrode is a glassy carbon electrode, and it is the surface functionalized with a molecular imprinted polymer. And the electropolymerization of the pyrrole monomer was carried out by the cyclic voltammetry in ethanol containing 0.1 molars of the lithium perchlorate in the presence of a template and considering the target molecules of anthracene. And then after extraction of the template by cyclic voltammetry, then this electrode was successfully used for the electrochemical detection of the anthracene. This is how this figure shows that. In the first step, we are doing this electropolymerizations, and then followed by the template extractions. So these are the selective electrosorptions, adsorptions of anthracene, and then these are the electrochemical oxidations we are carrying out, and that's how we measure the concentrations of the anthracene in the different water samples. So these are the various advantages of using the voltammetric technique. As we have seen that in my previous lecture, that we have both FAS, GFAS, and ICP OAS. These are some of the technique where we can go in a sub ppm levels. So again, in the case of voltammetry also, this is one of the alternate technique. We can use it here also. We can detect the many element in a one go, and the interference. Actually, these are the various interferences can be avoided there actually. Okay, and then here also, see, in case of the inorganic, as I told you in my first lecture itself, whenever we are doing any kind of inorganic, the analysis of the determination of any inorganic analyte in a matrix, in any matrix. So our first aim is that to destroy the organic matrix in that actually. And that's we can do by using the wet digestions. Or by the dry acting, if it is solid there, and then we can use this one. Okay, so here again also in this case, in the determination of the various kind of analyte by using the voltammetry also, here also we have to destroy the organic content, Actually, I do not know how many people that is called, say, dissolved organic carbons are there. See, and then in dissolved organic carbon, there are, two various kind of one is the low molecular weight compounds are there, and other one is the high molecular weight compounds are there. In high molecular weights, maybe, humic acid and fulvic acid. See, basically in the naked eye, we cannot find out because generally whenever organic substances are there in the system, you kind of some kind of, brown color feeling. But many times, the concentration is, although it's very small, you cannot detect by your naked eye, but there are concentration of organic compounds are there. So if those organic compounds are there, so they will interfere in all kind of analysis. So that's why it's necessary to remove those things. That can be done by using in case either hydrogen peroxide or even UV radiation also sometimes help us to remove these dissolved organic carbons. Then, of course, here also that taste determination that is well below this 10 raised to the minus 6 moles per liters. And one of the most important, unique and most important distinctions of this particular technique is that I think whether you had missed these words or not, we can determine not only the element, we can determine its chemical form. Chemical form, not in case of a valency as well as the various kind of molecules are there. So it can be, this is the only technique by which we can determine the chemical forms of the elements. By using the volumetric techniques are there. Okay, and generally compared to other techniques, the volumetric is less expensive actually, and it's a very very handy also. Not involved with sophisticated instrumentations for example, we need a air acetylene gas or nitrous oxide acetylene mixtures are there, and other case we need argon, and there's a large flame plasma will be generated in case of ICPOS. So those kind of a tedious things are not there in the volumetric techniques, and that's how all about this volumetry. So before going to the thermal analysis part, again I request you. I do not know how many people of you are listening now, right now, but if you have any questions during these lectures, especially about the volumetric technique or the electrochemical methods, please come forward and ask the questions. And because I'm not a user of the volumetric technique, because so far I use only for this analysis of the uranium only. Otherwise, I have not used so far. But definitely, if you have any particular queries there, I will ask my colleague who are the expert in this field to give you an answer. Mostly, I will myself able to satisfy your queries. If not, then I definitely ask my colleagues. Any queries? नहीं ना कोई है क्या? अमित भारद्वाज, अभी कोई है क्या? नहीं है. Hello?
She's not there.
She's not there.
Recording.
Okay. No, leave it there. Leave it. Okay. I'm really looking forward for your queries because if you ask some question to me, I will also come to know that how much I know. Because for us, basically, we are not a professional teachers, basically. We are working scientists. So, see, there is a vast difference between a professional teacher as well as a working scientist, actually. So, if your queries are there, definitely I may be knowing your answer and then I may be explained in a better way than whatever I given you in this lecture form. So, please come forward and ask me if you have any queries are there. So let's go to this thermal analysis part. See, thermal analysis, as the name suggests, see, whenever you are doing any kind of study with respect to the temperatures, okay, it comes as a part of the thermal analysis. Okay, so thermal analysis is the term applied to a group of methods and technique in which the chemicals or the physical property of a substance, a mixture of substance or a reaction mixtures are measured as a function of temperatures or time, while the substance is subjected to controlled temperature program. And over a dozen thermal methods can be recognized which differ in the property measured in the temperature and the temperature program. We'll see in the next PowerPoint. And this find a widespread use for both quality control and research application on industrial product such as polymers, pharmaceuticals, clays, minerals, metals, and alloys. So these are, various techniques are there. For example, thermogravity methods, we are looking for the mass. Then the derivative thermogravity, the first derivative is the mass change, that is called a DTG. And then is a differential thermal analysis, DTA, that is differential temperatures. DSC, we are looking for the enthalpy. And then thermo mechanical analysis, these are mechanical properties. So this how, various methods are there, and these are the properties which is measured by using these methods actually. So all these methods are done under the thermal analysis. And while carrying out all these measurements, whatever we have seen the above, the furnace atmosphere can be either static air or a continuous flow of a gas, that is purging. We call as a purging. And what are the example of this, atmosphere? Inert condition, you can use the nitrogen. And what will do the nitrogen? That is inhibit oxidation of the particular material, or a reducing condition. For the reducing condition, the furnace atmosphere must be purged with the help of a hydrogen. Then it's based on the principle. This is general thermodynamic relationship. So thermal analysis are usually run under condition of a constant pressure, and the underlying thermodynamic equation is the Gibbs-Helmholtz expressions, that is delta G is equal to delta H minus T delta, where the we are using an G is a free energy of the system, H is the enthalpy of the system, S is the entropy, and T is the temperature in Kelvin. And the general chemical reactions, that is A plus B, that is the two different compound A and B, they will give us a product of a C and D. And if any reaction is spontaneous, if delta G is negative and is at equilibrium, if delta G equal to 0 and does not proceed, if the reaction does not proceed, if the delta G to be positive. And thermal analysis involves the monitoring of these spontaneous reactions. And differentiating the Gibbs-Helmholtz equation with respect to temperatures, that T delta G by dt equal to minus delta S, show how to move from a stable situations where the delta G, stable situation means delta G is though negative but very, very close to 0, to one where the reaction will occur. Okay, and then with the increase in temperature means if the delta S value is there is a negative value is there, causing a delta G less than a 0, that is negative value. Means the increase in delta S value is more than 0, that is increase in entropy, and in that case definitely delta G must be negative. And when the delta S is negative, decreasing temperature will achieve the desired spontaneous reactions. decreasing the temperature in case of the delta is negative. Once the reaction is made to occur, the thermal analysis may be used to detect the process, yielding different and a complementary information that we will see that some of these informations which we get it by using the thermal analysis. Now, first, this thermogrammetry. Thermogrammetry is the study of weight change of a specimen as a function of a temperature or time. Now, in this case, what is happening? The temperature is increased at a constant rate for the initial weight of the substance, and the change in weight are recorded as a function of a temperature at different time interval. And what is used? This technique is useful strictly for transformations involving the absorption or evaluation of a gases from a specimen consisting of a condensed phase. And a plot of mass versus temperature, that is thermogrammetric curve or a thermograms, or we can call it the TG curves, permit evaluations of a thermal stability, rate of reactions, reaction processes, and sample composition. And measurement of a change in the sample mass with temperatures are made using thermobalance, and the balance should be in a suitable enclosed system so that atmosphere can be controlled. See, what are the various phenomena causing a mass change in case of a thermogrammetric analysis? So these are the physical changes are there. Either it can be gas adsorption. So in this case, mass will increase. Gas desorption, mass will decrease. Then the phase transition, which include the vaporization or sublimations. Whereas in case of chemicals, there can be because of decompositions, breakdown reactions, gas reactions, or maybe because of the chemissorptions. Chemissorptions, here what is meant by adsorption by means of a chemical instead of a physical process. This basis of this, what is we doing TGA, that is measure the change in weight relation to change in temperature, and the measured weight loss curve give information on the change in the sample composition, thermal stability, kinetic parameters for a chemical reaction in the sample, and the derivative weight loss curve can be used to tell the point at which the weight loss is most apparent. And these are the general considerations. A suitable sample for TG are solids that undergo one of two general type of reactions. That is, reactant goes wherever you do any kind of reaction on that, it can give you a product plus gas, so there is a mass loss. And then if there is any adsorption, that is gas plus reactant, then there is a mass gain will be there. So process occurring without a change in mass is not possible to use a thermogrammetry for studying that particular reactions there. So what is the most necessary thing? That there must be a mass change. So weight loss we are already seen that it can be because of the decomposition, evaporations, or reductions. Reduction means interaction of sample to reducing atmosphere, that is hydrogen or ammonia. Desorptions, and the weight gain can be of the oxidation, that is interaction of sample with an oxidizing atmosphere, or absorptions, absorbing something or being absorbed. And all of these are the kinetic processes are there. So kinetic processes are there. Then these again very important thing is as far as the TG is concerned, that is the instrumental factor, instrumentation factor as well as the sample characteristic. The instrumental factor may, that is the furnace heating rate and a furnace atmosphere. And as far as sample characteristics are there, weight of the sample and sample size. See, furnace heating rate, the different heating rate, you will get a different kind of a reaction actually. And similarly for the furnace atmosphere also, whether you want to keep it static or this inert atmosphere or a reducing one. That's what we have seen that we use in, they can use in nitrogen atmosphere, or we can pass with the hydrogen one. Similarly, weight of the sample, the weight should not be, we'll see in this coming part how this weight loss. The furnace heating rate, the temperature at which the compound decomposes depend on the heating rate. See, when the heating rate is high, the decomposition temperature is also high. And heating rate of generally, these are some of the optimal conditions, that is 3.5 degrees centigrade per minute is usually recommended for TGA to get a reproducible result. Whereas the furnace atmosphere, the atmosphere inside the furnace sound in the sample has a profound effect on the decomposition temperature of the sample. A pure N2 gas form is see, basically, whenever it has to pass through the from any kind of a cylinder to the furnace volume, and the sample characteristic weight of the sample. A small weight of the sample is recommended. Why? Because using a small weight eliminate the existence of a temperature gradient at least within the sample. So throughout the sample, you are maintaining the same temperature. And the particle size. See, generally we try to take the uniform size of the particles actually. The particle size of the sample should be small and uniform. The use of a large particles or crystals may result in apparent or a very rapid weight loss during heating. And this application of the TGA, from TGA we can determine the purity and thermal stability of both primary and secondary standards. Determinations of the composition of a complex mixtures and decomposition of the complex, and for studying the sublimation behavior of various substances. TG is used to study the kinetic of the reaction rate constant, and what are the applications we can use in the catalyst also. For example, in this methanol production, we are using this zinc chromate. So what are the changes are happening? The temperatures can be seen by this in this particular catalyst, that is zinc and zinc chromate. So what are the this optimum condition we have already discussed. Okay, so these are the modern commercial instrument for thermogrammetric analysis, considered a sensitive analytical balance. This is most crucial part of a TGA instrument, and these are the most expensive one also. A furnace and a pulse gas system for providing a inert or sometimes active atmosphere, and definitely a microcomputer processor for instrument control and data acquisition and display. And a pulse gas switching system is a common option for application in which the pulse gas must be changed during the experiment. So this is how this instrumentation look like. So this is basically one of these TG instrument, and these are the various temperature time program which we can use, and the sample size ranges from the 1 to 100 microgram, and the heating rate. But as I told you, the heating is better, always to be in the range of about 3.5 degrees centigrade per minute, because that will give you a better this one. Otherwise, you can choose provision are there that you can use choose any of these time here actually between 1 to 50 degrees centigrade. And one can study about these corrosion studies, gasifications, and the various kind of a kinetic process also can be studied by using the TG curve. This is basically TG curve for the calcium oxalate decomposition, and you can see that this is basically involved the three stages where the losses of the loss in weight is there. At the first stage itself, we are losing these water molecules. In the next stage, we are losing the carbon monoxide, and the third stage, we are losing as the temperature increases, we are losing the carbon dioxide. So this is basically derivative weighting curve, that is the DTA. And then, at the peak height, you are getting that maximum weight loss. And this is generally reactions going on. At the first temperature means about, say, 150 degrees centigrade, calcium oxalate will go to calcium oxalate plus water molecules. Monohydrate will go to calcium oxalate. Second stage, we get a calcium carbonate and a carbon monoxide. And a third stage, we are getting as a calcium oxide and a carbon. That calcium carbonate will further decompose to calcium oxide and carbon dioxide. Then comes this differential thermal analysis. What is the basic of the differential? The material under study and inert reference. Basically, in this case, not only we are taking the material which we are going to study, but along with the material, we are having a reference material, sir. And then we study the both thermal cycle of both the material as well as the reference material. And what we are recording in this thing, the temperature difference between the sample and a reference. And basically what we are measuring it, heat flow to the sample and reference remain the same rather than the temperatures. And this is how these thermograms will look like. And in this case, we know that crystallization, basically the exothermic reactions are there, whereas the meltings are the endothermics are there. So these peaks will be whenever we are measuring this dq by dt versus time curve, that is heat flow. So these peaks can be depend on the type of the instrument. They can be on the upper side or the lower side. That's what is written there. So the orientation of the peak in the thermogram may be reversed for this exothermic or the endothermic depending on the instrumentations. So what are the phenomena going on in the case of this DTA? Physical phenomena involve these adsorptions, which is exothermic, disruptions, endothermic, a change in the crystal structures, which may be endothermic or exothermic depending on this change. Then crystallization, which is exothermic, melting point again is endothermic, vaporations, endothermic, sublimations, also endothermic. And the chemical phenomena, the oxidations, exothermic, reductions, endothermic, breakdown reactions, again can be of either endo or exothermic, chemical options, exothermic, and the solid state reaction, endo or exothermic, depending on the thing that the curve of the dq by dt versus t will be getting various peaks are there. And this is how the schematic for this DTA instrumentations are there. So basically there is a two ports are there, but one is for the samples and other for the reference material. And then we are having this atmosphere controls, which can be atmosphere control and temperature programs and amplifier. And this amplifier we give to the data recorders, so where we get it our thermograms. So various kind of a reference material which we use in case of DTA, it can be magnesium oxide, aluminum oxide, or silicon carbide. And what are the characteristics of these reference material? Over the operating temperature, that they themselves should not go any kind of thermal event, and it should be inert toward the sample holder or a thermocouples, because it should not react with the container of this sample holder as well as the thermocouple, and the thermal conductivity and heat capacity should be similar to that of the samples. So it can be used for this, DTA can be used for the quantitative analysis, that the analysis of polymers, ceramic and metal industries, and phase transitions, for example, in case of a sulfur. And this is how this DTA curve look. Again, this is a calcium oxalate monohydrate. So yes, two which will not be when first water molecules, then the liberations of these carbon monoxides, and then these are the calcium carbonate will raise to the calcium oxide and the carbon dioxide are there decomposed into this one. Okay, so here basically this calcium oxalate will react with the oxygen and then will give us the calcium carbonate, okay, and carbon monoxide. And here what we have done, the heating rate of about the 8 degrees centigrade per minute. This is the DTA curve of calcium copper pentide in the presence of oxygen, and the heating rate is about 800. This by mistake it's 8 degree centigrade per minute only. And this is how, in the first we are losing only two molecules of the water, and when we increase the temperature further, we are losing the only one molecules, and when we raise the temperature into 220 to 250 degrees centigrade, we will release the another one more water molecules are there. So those are the three peaks which will correspond to this loss of a water molecules from the copper sulfate pentahydrate at a different temperature range. So what are the difference between the TGA and DTA? In TGA, we are recording change of mass sample with increase in temperature. Whereas in case of DTA, we measure the temperature difference between sample and the reference temperature, and plot a graph of a mass versus temperatures. What we plot is delta T, that is the temperature difference between the reference material and the versus temperature. The change in mass gives the information of in case of TGA, DTA, maxima and minima give information about the exothermic or endothermic process with the samples. Now we comes to the differential scanning calorimetry. So differential scanning calorimetry is just basically heat flow, and here also we are using this reference material. So what we are doing DSC measure the differential heat flow associated with transition in substance and a reference material linearly heated at a predetermined rate as a function of time and samples temperature in a controlled atmosphere. Okay, and these measurements provide quantitative and a qualitative information about the physical and a chemical changes that involves either endothermic or exothermic, or change in the heat capacity. And the differential thermal analysis is suited for determination of the characteristic temperature, while the differential scanning calorimetry additionally allows for the determination of the caloric values such as heat of fusion or heat of crystallization. And it's very, both in both these techniques, DC and DTA, sample and reference both are heated or cooled at a constant temperature, linearly at a predetermined rate. And during a thermal event in the sample, the system will transfer heat to or from the sample pan to maintain the same temperature in reference and a sample pan. See, in case of a DSC, we are maintaining the temperature should not be the same temperature. Both the reference material sample should be at the same temperature. And there are two basic type of DSC instrumentations are there. That is a power compression DSC or a heat flux DSC. And both differ fundamentally in their instrumentation. These are the differential scanning calorimeters, various parts of the involved in the differential scanning calorimeter. And this is basically just we are doing the study of the polyclean phthalate. And here we had increased the temperature, the heating rate is maintained at 20 degrees centigrade per minute, and the temperature range of 30 degree to 300 degrees centigrade are there. So we had both, we can record both this melting point and the this crystallization. And this is basically partial to show the glass transitions. I think you must be aware what is the glass transition in case of a polymers. And the last, we're discussing about this thermometric titration, as the name suggests. For example, we have seen the acid-base titration as well as the redox titration. Similarly, thermometric titrations are there. See the titrations which involve large change in the enthalpies. Okay, so this can be recorded as a change in the enthalpies will be recorded here. So in the thermometric titration, titrate is added at a non-constant rate to a titrant until the completion of the reaction is indicated by a change in temperature. And the endpoint is determined by inflection in the curve generated by the output of the temperature measuring devices. So this is basically considered a reactions, that is A plus B gives a product of P plus and then heat. Okay, so A is the titrant, B is the analyte, and P the product. Okay, so its corresponding moles are there, that is the coefficients. At completions, the reactions produce a molar heat of a reaction, that is delta HR, which is known as a measurable temperatures changes. And in the ideal system, where no loss or gains of heat due to environmental influence are involved, the progress of the reaction is observed at a constant increase or decrease of temperature, depending respectively on whether the delta HR is negative, indicating an exothermic reaction, whereas a positive, which indicate an endothermic reactions. And these are modern instrumentation. This is a conventional one. Now the modern instrumentation, which is from the metron, used for the thermometric titrations. And various all these titration can be done this HCl versus NOS and boric acid versus NOS, and the titration of calcium and magnesium versus EDTA. So those titration can be done by using the thermometric titration also. Means the concentration of can be determined of HCl and boric acid or calcium magnesium by using either NOH or EDTA by using the thermometric titrations. So this is how this curve look like. Okay, this is the titration of HCl versus NOS, and the heat of basically this is the heat of utilizations of a fully dissociated acid with a fully dissociated base is approximately minus 56 kilojoules. Here again, the calcium reacts exothermically with EDTA, and heat of chelations is 23.4 kilojoules per mole, and magnesium react with endothermically with a heat of chelation about the plus 20 kilojoules. So this is how we have done the determination of both the calcium and magnesium in sample by using the thermometric titration by using the EDTA. So thank you. Again, I am requesting you, if you have any queries, please come forward. Because while giving these online lectures, the lecturer will not come to know whether you are able to understand or not. And not being a professional lecturers, very difficult to understand whatever we are telling. Ask any queries, email ID also with you. You can write your questions or your queries about the subject, and then I will very few answer your queries. Is there any questions? Both are not there. Actually, last time it's better now. अभी क्या this goodbye. and then we'll meet. You can unmute mic. Hello, you can unmute your mic. Any one of you are there? Okay, you on Friday. Okay. एक्चुअली क्या होता है, सामने अगर बच्चे बैठे होते हैं तो उसको बोल सकता है, क्या समझ में आएगा, ये क्या है।